Today we're going to talk about controlled experiments and their variables. The first question you have to ask yourself is, what exactly is an experiment? Well, an experiment is a test for your hypothesis, and typically it's going to be controlled. If you remember, a hypothesis is an if-then statement that seeks to explain something. So what do I mean by controlled? Well, a controlled experiment keeps everything the same but one variable. Think about it. If you changed 3, 4, 5 different things, how would you know which one got your result? If you were, let's say, a race car driver and you changed 5 different variables on your race car and it ran really well, which one of the 5 caused that to happen? So in controlled experiments, we keep all of those variables the same so that we know exactly what changed. Take a look at this picture. Pretty iconic for at least a middle school experiment. A lot of students are familiar with the volcano. You mix a couple things and out of the top of the volcano that you've made comes lava. But is it really an experiment? We'll take a look at it a little bit later. Let's talk about the parts of a good controlled experiment. First and foremost, we'll have an independent variable, often just abbreviated capital I, capital V. The independent variable is the variable that you change. You're going to manipulate this variable to be whatever you want it to be. If we're talking temperature, you could be setting the temperature of a refrigerator at 30 degrees Celsius and then another one at 15 degrees Celsius. Which one do you think would keep the food better? That is an example of an independent variable. You change it, you set it. The next variable that's in a controlled experiment is a dependent variable. That's a variable that you are actually going to measure. It changes because of what you did to the independent variable. So if you're looking at how good food lasts in a refrigerator, you would measure how long it takes something to spoil. If in the one where it was 30 degrees Celsius, it only took a day to spoil, and the one that was 15, it took 3 days to spoil, you know that the one with 15 degrees Celsius obviously is better for keeping food. But you know that because you measured a dependent variable. What did you measure? How long it takes the food to spoil. So an independent variable is what you change. The dependent variable will change, but it does so because of whatever you did. It happens on its own in the experiment, and it typically is what you're looking for. In experiments, we like to collect data. You notice I said how many days it took food to spoil. That's data. It's information that you record based on measuring the dependent variable. So, some examples of an independent variable could be temperature, like I used, could be time of exposure, could be nutrients, could be water. All of those can be things that you can change. Are there other independent variables that you're able to use? Absolutely. Those are just some examples. Dependent variables that you might measure could be mass, length, height, concentrations. That one's pretty common when you're talking about acids or bases. It can also be population number and temperature. You know, you're saying, hold on, Mr. Burns. If temperature is an independent variable, how can it also be a dependent variable? Well, it depends on the situation. If you're changing it, that is you, the scientist, then it's an independent variable. But if it changes because of something else, then it's a dependent variable. For example, when I was in college, we did an experiment where we changed different things in a glass box to see which one would help insulate it better. We measured insulation by looking at the temperature. We weren't changing temperature directly. What we did do was add more insulated walls, reflectant aluminum foil to keep the light in there. Those were our independent variables. The dependent was temperature. So sometimes a variable can fit in both categories. It just depends on the situation. And of course, for data, typically speaking, we're going to organize that into a table, make it nice and easy to look at. So let's go back. Is this an experiment? The first question I have for you is there an independent variable? Did they manipulate something? In most cases, no. They just mixed a couple ingredients and they got some fizz coming out of the top of their volcano. Did they make any measurements? In most cases, no. They're just watching it. It was just for the excitement of it. They're not measuring anything. So because there's no independent variable and there's no dependent variable, I would say this isn't an experiment. Much more of a demonstration or a model. Definitely not an experiment. You have to have an independent and a dependent variable. So let's look at these two samples, if you would. Grass A and grass B. Clearly they're different. Go ahead and make observations, then make an inference and a hypothesis as to exactly what's going on here. You have your hypothesis done? Well, let's take a look at it. We talked about making hypothesis before, but let's see if we can make that hypothesis better. First off, it is an if-then statement. If something, then this will happen. A good hypothesis actually includes your independent and dependent variable in it. For example, if the amount of sunlight is increased, then the grass will grow higher. One of them is my independent variable, and the other is the dependent variable. An easy way to spot the independent variable is, which thing are you changing? And of course, we're changing sunlight. Easy way to spot the dependent variable is, what are you measuring? Of course, we'll measure the height of the grass. So the independent variable is sunlight, the dependent variable is the height of the grass in millimeters. I've included a unit because I want to be very clear as to what I'm measuring. Your hypothesis might have been different, but if it didn't include an independent and a dependent variable, go back now and correct it. Our data is what we're actually going to measure. Again, that's our dependent variable. It should be embedded in there, but if you did like I did and you put your dependent variable in there, it should be quite clear. Talking about data in science can be a little different than other classes. Oftentimes when you talk about something like height, you might measure in inches, like here. But in science, we're going to use our metric data system. It doesn't actually use inches, feet, yards. It actually uses millimeter, centimeter, meter, and kilometer. The advantage of using the metric data system is that everything's in the power of 10. So 10 millimeters equals 1 centimeter. 100 centimeters is 1 meter. 1,000 meters is a kilometer. And of course, there are groups in between there, but these are the most common ones. I chose millimeters for the grass because I want to be very, very accurate. And down here I have a ruler. You can see 10 millimeters. 10 millimeters is equal to 1 centimeter, which means 20 millimeters must be equal to 2 centimeters, and 100 millimeters must be equal to 10 centimeters. The metric system is fairly simple, and that's why we use it. So let's talk about a controlled experiment. Remember, all but one of the variables is the same in a controlled experiment. And there's more to it than that. Repetition and quantitative data are very key parts. Well, repetition simply means you're using more than one test subject. Let's say we look at a tree and we're experimenting on a tree. How do we know the tree we're looking at isn't some freak tree that does weird things that's completely different than any other tree? That's where repetition comes into play. If you're going to do a good experiment, you'll use 5, 6, 7, 100 different trees. That type of repetition, you'll clearly be able to see if you have a weirdo tree that's doing something different, because you have more than one. Repetition is very important. You don't have to necessarily do 100 in a class like high school biology. A real researcher would do much larger than 100. But for our sake, 5 or 6 is nice for repetition. Quantitative means that you got a number. So if you're going to have quantitative data, it's an actual number attached to it. So if we go back to my grass example, I was measuring in millimeters. That's quantitative. The example would be 5 millimeter tall grass. It's very clear what 5 millimeters is. There's no way to get confused about it. The opposite of quantitative data is qualitative data, and you want to stay away from qualitative data. It's more of a description. That would be like saying the grass is healthy. Well, what does healthy mean? Does that mean it's more green? Because if it's more green, then we should measure the wavelength, because that's very, very quantitative. What is more green to one person might not be considered more green to another person. So if we don't use green for healthy, maybe we're using size. Well, if we're using size, why don't we just do mass? You can see how using something like healthy, a qualitative or descriptive measurement, gets kind of hairy. It gets kind of confusing. So we want to stay away from those. We always want to measure something when we're doing an experiment. So let's go back. Looking at grass A and grass B, I now want you to use what you've learned to design a controlled experiment to test your revised hypothesis. Remember, your revised hypothesis includes independent and dependent variable. Don't forget to use repetition, and don't forget to make sure to use quantitative data. Design your experiment in a very detailed manner so that I can see exactly what you think it should be.